So I'm William Sexton. I'm a scientist at Tumult Labs. This is joint work with a lot of other people, and I'll get right into it. So we're talking about a case study of differential privacy with county business patterns, which is an annual series that the US Census Bureau produces that produces aggregations about businesses such as annual payroll or employee sizes, grouped by a number of different categorical characteristics like geography or NICS codes, which are industry classification codes, like is my business a retail business or a construction business or a shoe store or whatever. And so the challenge that we faced is we want to accurately release these economic indicators, and we want to use modern, formal, mathematically rigorous privacy protection to release statistics from tables like this. But we're dealing with highly skewed data. And so an example here is I want to release a payroll sum of 4 establishments with values like 1,000, 2,000, 5,000, and 4 million. And the takeaways from my talk, I'm putting them up front, is that differential privacy just is not a very good fit for this problem. And that's not a flaw with differential privacy. Like that's differential privacy working as intended. So differential privacy is really, really good if you're trying to hide needles in haystacks. But it's not so good if you're trying to hide fire trucks in haystacks. And so we want to kind of rethink our privacy notion a little bit. We still want to get formal privacy guarantees, but we want to be able to say something new, more nuanced. So the problem with differential privacy is that if I'm trying to hide needles and fire trucks, I get like basically a global privacy guarantee at the end of the day that applies to all of the objects that I'm trying to hide. And we want to say something more nuanced where we say, okay, yes, the fire trucks are maybe visible in the haystack, but we're still getting strong protection for the needles that are in the haystack as well. And so that's our goal. So we have a new interesting technique to handle this that gives us high data utility with this formal privacy protection, but it does come at a cost. It's definitely a relaxation of the usual notion of differential privacy. And so I'll describe this relaxation through a baseline mechanism that we developed. And so we're going to look at this question of counting the number of employees that work in a particular zip code just north of Reno, Nevada. And if I look at this zip code, there's a bunch of these large contributors in this area. Sherwin-Williams, JCPenney, several Amazon warehouses, a Walmart supercenter, and traditional differential privacy would tell me that I essentially have to calibrate my noise based on the properties of these large contributors. But we want to flip things around and think about the smaller contributors first. And so we have this taco place that I've highlighted here. And we really want to set our noise scale, decouple it from the large contributors, and set our noise scale to focus on hiding these smaller contributors first. And then we're going to think about what that means for these larger guys. And so I'm going to think about hiding these guys actually kind of in pieces. So if I have 100 employees at this Sherwin-Williams, I'm going to think about hiding like 25 employees at a time. So I hide 25 there, another 25, another 25, and so on. So I'm going to hide this in pieces. And so then intuitively, the idea here is that we're relying on a concept from differential privacy. We're not like fully reinventing the wheel, but that's called group privacy. And so group privacy says that if I have an epsilon DP algorithm, I can extend its privacy guarantees to groups of size k. And basically I pay a cost of doing that. So my privacy loss, instead of being epsilon for these larger groups, it's k times epsilon. And so if I talk about that Sherwin-Williams, I broke it up into 4 pieces. That would mean that its privacy loss is 4 times the privacy loss of some business or establishment that was not broken up at all during this process. And the JCPenney's might be broken up into 12 pieces, and so it's got a 12 times privacy loss compared to these other guys. And so this allows us to give a tailored privacy loss claim based on the characteristics of the establishments that we are protecting, and with the goal really being able to make strong claims about like a majority of establishments, but then there are going to be establishments that suffer worse privacy loss as a result of this. And so our definition that we've developed in a more abstract sense, we call per record differential privacy. We think about adding or removing a particular record from our database, and then we're going to get a privacy loss bound that's a function of that record's properties. And so standard differential privacy is a special case of this, where the function is a constant. But in our example algorithm that we gave, we have a pre-processing component where we split our database up into like sub-establishments, and then we apply a DP mechanism on top of that, where the unit of privacy is these like smaller components of our of an establishment, and the privacy loss function that we get is just like the number of pieces that a record got split into times epsilon ends up being that record's privacy loss. So how does this work? What are the trade-offs between privacy and utility that we see when we do this? Because this fundamental trade-off still exists. It always exists with like every DP like variant. Basically, if we look at an example from this data set, so in the left-hand column, I have like a standard deviation of the noise that's being added, and there are like a number of parameters that can factor in to these standard deviations. And so, so I'm presenting it this way, but yeah, you could have like different privacy loss values, and different like mechanisms for splitting up your data that can all lead to the same standard deviation of noise. And so that's what we're focusing on here. And then we're using coefficient of variation as a measure of accuracy or utility here. And if we look at, as an example, a standard deviation of 500, then when we get into cell sizes that have 10 or more establishments in them, then we see better utility than what you would get from out of a traditional differential privacy approach to this problem, and so that's very nice. On the flip side, so we're going to look at this concept that we're calling relative protection, and this is just kind of an ad hoc, because epsilons and rhos and values and Greek letters are, like the last talk mentioned, it's abstract, and a lot of people have a hard time grasping it. And so this is something that's resonated with people, but we're just looking at a measure where standard deviation of the noise added over the like value of the establishment, and this is like a sanity check to make sure that we're on the right track here. But when we look at, again, that example, standard deviation of 500, then something like 99% of the establishments in our data set are receiving kind of strong privacy protection according to this measure. But the downside here, again, is like those fire trucks are still visible. And so if we think about like a small establishment, maybe it has an annual payroll of 2,500 or 250,000. that's an establishment like that is going to get this like strong relative protection measure, but an establishment that has 500 million for their annual payroll is going to get a very weak relative protection measure. And so this is an ongoing journey. The case study is like not at the end of its life cycle. We've released with the Census Bureau some demonstration data using this methodology, but we're still looking for ways to improve it. And so two of the questions that we're looking at for the future is whether we can basically build directly algorithms or mechanisms that satisfy this new notion of privacy instead of, so our current method is more indirect where we're falling back on a lot of properties of differential privacy. But we'd like to see, can we build a mechanism that has sublinear growth in privacy loss? And then the other question is, can we incorporate something like the high dimensional matrix mechanism into this workflow to optimize privacy loss across the large quantity of queries? So the county business patterns, for example, is measuring, there's something like 8 million establishments in this data set, but the Census Bureau releases something like 800 million cross tabulations out of this data. So even with this new methodology, your privacy loss can start adding up very quickly when you're releasing multiple sequentially composing queries. And so we'd like to look into methods to sort of improve or mitigate that as well. And so thank you.